We're just doing, it's a very short unit, as some of you have already noticed. I know you've been mentioning it to me. There's only 3 homework assignments. There's 3 topics. We're going to be taking our next test a week from this Friday. So it's very, very quick. And this is our last unit, and then it's all review after this. I was going to say, what was I going to say? Oh, the topics that we're doing in this unit are not on the AP exam. They're actually on the BC exam, not the AB exam. So it's all for fun, but it does count towards your grade. But it's only 3 topics, so hopefully the unit test, I mean, the unit test could still bring up some stuff from previous units, but hopefully because it's such a short unit and very focused, hopefully you'll find Friday, next Friday's unit test celebration a little bit easier than we've had. But yeah, let's do with Euler's method first. So what is Euler's method, you may be asking yourself? Well, I will, hang on, I already have it written down very nicely. Let me get my notes out here. Here is what Euler's method does for us. Euler's method, and yeah, it is pronounced Euler, even though it looks like Euler. So Euler's method produces a numerical approximation to the solution of a first order differential equation. Oop, can't spell equation. Oh my goodness. Given an initial value. What does that mean? Basically, when we had those differential equations, where you had it had a derivative in it. And first order just means it only has a first derivative. A second order differential equation goes up to a second derivative. A fourth order differential equation goes up to a fourth derivative. So first order means the highest derivative that the equation has is the first derivative. And we looked at one way of solving differential equations, which was separation of variables. That was on your last test. But what if you can't solve it? Because not all differential equations have a nice solution. Well, if you can't solve it, but you still need to find a value for the equation at a certain point, Euler's method does it for us. Have you guys ever seen the movie Hidden Figures? See a couple of. We'll actually watch it after the AP exam because it's a great movie. And have you guys heard of Hidden Figures? Oh my goodness. This is very sad to me. A few people have. Hidden Figures is actually it astounds me that is a part of our history that I had no idea about until the movie Hidden Figures actually came out. So back when the space race was going on, NASA was just getting its start. We actually there was a group of women, group of black women. They were called computers back in those days. Basically, they were people that just like did a bunch of number crunching, a bunch of calculations, but by hand because we didn't have fancy computers or calculators back in those days either. So the people that did it were called computers. And there was this group, they were, first of all, they were women. So that was really cool. And there were, group of women that were not black, but there was also this one group of women that were black and the impact that they had on the space program back in those days. Like it's actually a really, really great story. So it's all true. But there's this one part, they did take some artistic liberties, of course. But there's this one part where they're trying to solve a problem and they can't figure it out. And they end up using Euler's method. And that part, actually, I read up on that. So I was like, is that part really true? Apparently that's one of the artistic liberties that they took. But it's an example. Even though it didn't actually happen, it could have. It's like totally realistic. But anyway, how does Euler's method actually work? Well, I'm going to steal some pictures that I've grabbed. We've actually seen these pictures on our notes before. But yeah, don't worry. You don't have to actually make slope fields. That's a good news. But remember the process that we did by hand. Like if we wanted to know what the actual equation was that went through that point right there, then the idea was to follow the flow of lines. And what Euler's method does is it basically follows the flow of lines with a very specific algorithm. So, for instance, the slope of this line is going in this way. So I'm just going to basically follow that slope until I get to the next one, and then follow that slope until I get to the next, follow that slope until I get to the next, follow that. So I don't actually come up with an equation for the solution, but I can still come up with an approximation of where that solution would go through. And here's a better picture of Euler's method. Bring that up. Okay. So again, you can see that kind of following the flow of lines until we get to the next point. So it's also starting here actually at t sub 0, y sub 0. So following it until we get to that point, following until we get to that one, following until we get to this one, following and so on and so on. It kind of ends up doing this. So your initial value is actually on the solution. So you know that point. But you take these steps. So if you notice, like every time we go to the next value, our x value is either increasing or decreasing by a constant amount. So that delta x is actually, we call it h. That's going to be our step. So h is how much you're changing by x each time. So this point here is at x0, y0, and then we multiply by h to get to the next point and so on. I'll talk about this notation in a second. But it does, the further away you get from that initial point, that initial value, the worse and worse your approximation is going to be probably. So we're getting further and further away from the exact solution. But it gives us a way of approximating. So that's the idea behind Euler's method. Now, like I said, we're not actually going to use slope fields. We're going to use an equation. We're going to come up with an equation that does this process for us. And then once we have the equation, the calculators will actually be able to do it for us very nicely. So I'll be showing you that. So any questions about the idea of Euler's method and what it's going to do for us and how it works? Okay. So before we get into Euler's method, let me just do a little notation here. Notation. Derivatives. We actually already know some notation for derivatives right now. We have dy dx. We've been using that probably predominantly this year. And then similarly, we can just say taking the derivative of some function, d dx of f of x. But we've also seen y prime. And these are the notations we've seen for the first derivative. But there's another one that's used commonly with Euler's method. The one thing about all three of these methods is your derivative, if you're going to say dy dx equals, or d dx of f of x equals, or y prime equals, it's kind of assuming that you solve this derivative and that your derivative, I mean, it doesn't have to be in terms of x and y, I mean, only x. It's kind of assumed that you're probably going to be writing your answer in terms of x. But another notation looks like this. A capital F with xy. And that also means the derivative. It's the first derivative in terms of x and y. And we're going to use that notation for the first derivative because our first derivative is often given in terms of x and y when you're doing Euler's method. So this means the first derivative in terms of x and y. So now that we got that notation out of the way, let's see how Euler's method works. So to derive the formula for Euler's method, we're actually going to start with point slope form. Derive Euler's method. It's a very quick, easy derivation. We start with point slope form. Y minus y1 equals m times x minus x1. Point slope form. Anybody still need the derivative notation stuff? Okay. So we start with that, and I'm just going to go ahead and solve for y. So y is equal to y1 plus m times x minus x1. But x minus x1, that's like a change in x values. So that's like a delta x. So I'm just going to say m times delta x. And then delta x, I don't know if you caught it when I was describing Euler's method given those pictures, but our change in x, when we use Euler's method, you typically see h used. H is just your delta x. I'm going to put a little note here. So h equals delta x, but often what you'll hear it called, you'll hear it called the step. Called the step. You'll see when I give you an example of how it's used in context, but it basically says, you know, like use Euler's method to solve this, blah, 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 using a step of 0.1. It just means change your x values by 0.1 each time. And then m, derivative, slope, rate of change. It's our derivative. And now we're going to use that notation I gave you with the capital F. And this is at that point, x1, y1. And that's actually pretty much it. I'm just going to change one little thing, and I'm going to write, so here's the actual Euler's method formula. So y sub k plus 1 equals y sub k plus h times the first derivative in terms of x sub k, y sub k. And there's our cloud. Our one and only cloud today, because it's going to be such a nice, sunny, beautiful day. So Euler's method is an iterative process. If you're a programmer, you might have an idea what I'm talking about with an iterative process. If you don't worry. What it just means it's a process that repeats itself. So this y sub k plus 1, think of that as the next value of y. And then the x sub k and the y sub k means the current value. So you evaluate this right-hand side at the current values of x and y to give you the next value of y. And then you do it all over again. Now you evaluate at the new values of x and y to find the next value of y. And then you keep doing it again until you get to where you want. You'll see that in practice. So that's it. There's probably some questions. So I don't know if anybody wants to ask them, but I may not answer right now. I may say, yeah, well, I'll explain that with their example. But does anybody have any questions they want to ask right now? Okay, let's just do an example. Yeah. Yeah. Example. Let y prime equal sine x cosine y. Y of 0 equals 0. use Euler's method with a step of h equals 0.1 to approximate y of 0.5. And we're going to do this without actually finding a solution to Euler's method. You will often see people put their information in a table. As far as showing your work goes, even if you're using a calculator, please put your work in a table because then I can give you partial credit. It's a very simple table. We're not going to use a calculator in the beginning. Well, if we are, but we're not. So here's what the table is going to look like. Go green. We're going to use n, x sub n, y sub n, and then y sub, n plus 1. That looks funny. And just for a visual, I actually like to put the equation for y sub n plus 1. And we're going to use the cloud for that. But we're also going to plug in for h in our derivative. So according to the cloud up above, the next value of y should be based on the current value of y plus h, which according to this problem is 0.1 times the derivative evaluated at the current x and y. And so the derivative is sine x cosine y, so I'm going to say sine x sub n cosine y sub n. And that's why we're going to be putting in our calculators every time. So those are the columns of our tables. I'm going to put some columns here. Actually, I want some room for y sub n to have some decimals. There's going to be a lot of decimals there. All right, let's see what this is. So we're going to start at our initial value. N is 0. And so x sub 0, y sub 0, those are our initial values. Anytime you see a variable with a subscript of 0, just think initial value. So our initial value of x is 0, and our initial value of y is 0. And I'm getting that. And now, let's plug into our calculator. So on my calculator, I will be doing, let's see if we can do this. Might be able to do this first one in our heads. Oftentimes, the initial value is easy enough to do in your heads. If we let x sub n and y sub n both be 0 in this equation, can you guys see what we're going to get? Yep, coming 0. Y sub 0 is 0. X sub 0 is also 0. So then sine of 0 is 0, which makes this whole term 0. So 0 plus 0 is 0. Doesn't seem like we got anywhere. But you'll see now, the next step we will. Any questions where that last zeros come, or any of the zeros are coming from? So then our next value, n is going to just increase by 1 every time. Anybody know what I'm going to put in for the x column? Point 1, exactly. Remember, h is our change in x value. So that's just going to tell you what your x's are going to increase by every time. In fact, The problem wants us to go all the way up to find y of 0.5. So we're going to let x equal 0.1, 0.2, 0.3, 0.4, and 0.5. And we'll stop there. Whatever the y value is that we get, that's going to be our approximation for y. And we know to go up by 0.1 because that's our step. So that's what the step means. So I can go ahead and fill in n, because n just goes up by 1 every time. But now to find y, that's where all the work on your calculator is going to come in. We do know the next value for y will be 0, because this is y of n plus 1, or y sub n plus 1. That was when n was 0. So y sub 0 plus 1, or y sub 1 is equal to 0. So now that we're here, this is y sub 1, it equals 0. So the value that you get here for y will go into the next line for y. Always. And then we just evaluate again using these new values for x and y. So if we plug them in here, it's going to look like 0 plus 0.1 times sine of 0.1 cosine 0. For purposes of this, of our notes, I'll go ahead and put it here. So this is y sub 2 will equal y sub 1, which is 0, plus 0.1 times sine of x sub 1, which is 0.1, times cosine of 0. And we'll see what we get. So does it make sense where I'm getting all of these values from? Oh, no, I do have first. So we just evaluate it. This is where we definitely need a calculator. Make sure I'm actually in radians. Make sure your calculator's in radian mode. Anybody get an answer they want to share? Did you get something like 0.0099833? And that's all I got room for, so I'm going to stop. Now, I'm going to show you, I want to fill in this table first, but then I'll show you again. I'll pull up my version of the calculator. But this value will go right here. So whatever you get for y in the previous row goes into y for your next row. But the question is, God, how many digits do we have to do? Do I have to type in all those things again? And the answer is no, because your calculator can do it for you. So let me go ahead and pull up my calculator here. So we had 0 plus 0.1, hopefully I'm in radian, I forgot to check, times sine of 0.1, cosine of 0, and we got this. So that's my answer, and that's what I want to use for the new value of y. So when I go into my next line, I mean, luckily x is easy. X just goes up by 0.1, so x is now 0.2. So y sub 3 is 0.009, I'm just going to put that, plus 0.1 times sine of 0.2 now. cosine of 0.009, but I'm not going to use 0.009 on my calculator. I'm just writing that down. But any questions where this is coming from? Because I want you to understand what I am going to do. So these 0.009s are really our previous answer. And I don't know if you guys have noticed on your calculator above the negative button, see how it says ANS? That refers to the previous answer. So it's going to look like this. I'm going to do second answer. I want the previous answer plus 0.1 times sine of 0.2 times cosine of the previous answer. So I can do that second answer again. I mean, the calculator is still rounding, but it's got a lot more digits than we can actually see on the screen. So it's a pretty darn good approximation, even though it's rounding. And then I get a new answer. So any questions on what I just did there? So let me record that 0.029. And then for the next lines, I'm not going to bother, and you don't have to. I'm just going to for our notes having this whole equation written here. All I really care about that you put in this last column is the value of y. But for the next column, for this y, I am going to put that answer plus 0.1 times sine of 0.3 times cosine of the previous answer. And so the only thing that I'm really changing in it is sine. Because now the calculator, when I type in ANS, it's going to use this as my previous answer. So I don't have to retype that all in it. All I have to do is just go back in and change the sine of 0.2 to sine of 0.3. So I got that back up on the screen, and then change the sine of 0.2 to 0.3. So it's kind of nice. Does that make sense? And I hit enter, and there's my new value for y, 0.059. And then I'll go back here, and I'll do it again, second enter, and I'm going to change 0.3 to 0.4. And I get 0.098. And then, oops, I forgot the O. Woo! Oh, 98. And I'll do it again. I can get on the 0.4. There we go. And I get 0.145. So now I have my approximation for y of 0.5. So does that make sense? So you can use your calculator, even though it seems like it's easy. I mean, if we actually had to type everything in, it would be pretty darn tedious. But kind of nice. All we have to do is just change the x value. So what's my approximation for y of 0.5? It's not 0.145. Exactly. Watch out for that. This is going to be one of the most common mistakes students will make, is they'll go too far. The answer is 0.098. This right here was our answer, because that was the y value for next to 0.5. So watch out for that. This is the next y value. This is going to be our approximation for y of 0.6. I didn't need to do that, actually. This was not needed. So beware of that. That'll be the most common mistake. The most common mistake actually will be on the test. Students forget the formula. Maybe the most common mistake is people put a minus sign instead of a plus sign there. But besides just forgetting the formula, the most common mistake is going too far. But that's it. That's Euler's method. Any questions? I'm going to show you an even quicker way that the calculator can do all this work for you. What? This was pretty quick. But no, it gets better. Because on your homework, and I do expect that you do it, we had to go up to 5. I mean, your homework only has, if you look at the sheet I gave you with like 6 problems or something, there's not that many. Your homework is not long. But you do have a couple of problems where you have to like have 10 rows in your table. But the calculator's doing all the work. All you have to do is just record. It's actually going to be more time consuming to actually write everything down than it is to actually do the problem. But please, please, please do this for me, because what often happens is, well, actually, let me tell you bare minimum. What I do want to see on a test to be able to give you full credit, I need to see, I already have stuff highlighted. Well, anyway, I want to see these rows, just the values, and include the entire formula, just so that I know you know Euler's methods formula. And then you just need the values. You don't need anything else. But I do want to see the formula. But what happens a lot of times, they always say what's the formula, they don't always give me the formula, and they're using the wrong formula. But if I can see all these individual values in there, I can usually figure out what you were using for the formula. And like I said, the most common mistake is people put a minus sign instead of a plus. But without those individual values, I can't always tell what you're doing. And sometimes what happens is students are doing the shortcut on their calculator. So maybe they have the correct formula, they have all of the x values correct, but like maybe writing down this y value, they put 0.0998 instead of 0.0098. So then when they type it in their calculator every time, they put in 0.0998. So they're using what they put on the paper, and that throws the rest of the values completely off. But if I knew what they were doing, then I'd go, oh, oops, that's a little mistake. You got the idea of what it is, you get majority of the credit. So I really need to see those early remaining values as well, even though it's a tedious process to have to write them all down. Okay, the last thing I'm going to do is just show you an even shorter method on the calculator. And if you remember it and can follow it, it's quite handy, especially when you're doing your homework. So any questions on this before we do that? Because there's really nothing else to Euler's method except this. It doesn't get any harder. Okay. Let's just make up another problem. Example. Y prime equals, I don't know. How about sine x plus cosine y? So I'm changing the problem ever so slightly, and we're going to use the initial value problem, or the initial value of y of 0. What would y of 0 equal? Yes. We're going to approximate. And we're going to do this one. I'm going to go out, let's say x of 0.8 using a step of 0.2. And I lost my train of thought. I'm going to just write down the bare minimum that I would want to see on your paper. But I'll also separately like put the steps for using the calculator. All right, so we're going to do this. I'm going to make my table. I still want the table set up, so we're going to have an n, an x sub n, a y sub n, and a formula for the next value of y. Yes, Marcus. Oh, whoops. Yeah, I don't know why, but that, thanks. We're finding y of 0.8. Make sure you change that. That's a weird mistake. Anybody want to give me the formula we're going to use for this one, for the next value of y? Rena? Did I get it right? Oh, so what I have written is good? One little thing we have to change. Joshua? Yeah. So where you got the 0.8, that's where the step should be. That should be the h. So this will be 0.2. Everything else is good. Excellent. And I'm just going to go ahead and set up, we're going to start at that. So x starts at 0. Again, in this case, doesn't always have to start at 0. And then I'm increasing by 2 each time, or 0.2. So we're going to go to 0.2, 0.4, 0.6, and we're trying to find when x is 0.8. So we're going to go up 4 times. So I have everything that I can fill out right now without calculating anything. When you're filling in your table, I think your book actually asks for 4 digits, but in general, if it doesn't ask, give me 3 decimal places. Again, practicing for the AP once 3. Maddie, did you have a question? No. Okay. All right. So we saw that we were kind of doing the same thing over and over and over again. We just had to make one small change. And so that's what we're going to do on the calculator. Now I'm going to kind of build this slowly. Like if you're a programmer, I could probably just give you the formula and it would make sense right away. But I'm going to go ahead and just kind of build this slowly. It's not a fancy formula at all, or it's not a program even. But anyway, so here's the idea. We're going to take that formula, and that gives us our new value for y. So I have to start off with my initial values. I have to tell the calculator what x and y equal. So remember, we've got this store button above I, where you can store values into variables. So I'm going to store 0 into x. Oops. In a different mode. Oh, by the way, if any of you guys, because my BC kids were using the calculators, see how, excuse me, right now when I hit the button that normally gives us an X, I'm getting a theta. If you borrowed one of my calculators, if that's happening to you also, you have to change your mode. Go to mode and make sure you're in function mode. So if that's, sorry if that's happening to you. So I want 0 store X, and now I'm getting X again. And then was it 1? I want 1 stored into y. And y is above the 1. You have to hit the alpha button before you get that. So now the calculator knows our initial values. And so now I can actually use variables to type this in. Our next value of y is the current value of y plus h, which is 0.2, times sine of x plus cosine of y. And here's the cool thing we can do. This is going to be my new value of y, right? So before I hit enter, I'm going to take this and store it into y. So now when I hit enter, there's my new value. So now, if I type in that equation again, when it calculates using y, it's going to use this new value. Let me go ahead and just quickly record this value. 1.108. So does that make sense? Now I do have to change x. Unfortunately, x has changed, and there's nothing right now that has changed x. As far as the calculator is concerned, x is still 0, but y is now that new value. So I do have to increase x. So 0.2 into x. And then you can either, I think most of you have figured out, you can move your cursor up to the old equation, or I just hit second enter. If I can get it. There it is. Finally. And now it's going to calculate using those new values. And now x is going to be 0.4. Now that I've done this, it won't take long. 0.4 into x. And there's my next new value for y. And so on and so on. I'm going to be able to make it even faster than this, but 1.237. Let me record these values. 1.380. So I only have to do this one more time. So now x is 0.6, and then second enter, and there's my last value for y that I need, 1.531. So y of 0.8 is approximately 1.531. And I'm going to show you an even better way. We're going to like almost automate this. But any questions on what I was doing with the calculator here? Because I'm just going to tweak it a little bit. All right, I'm going to clear everything out again. We're going to start from scratch on this problem. So our initial value was x was 0 and y is 1. So 0, you still have to set your initial values. There's no way around that. So 0 into x, and one thing that's nice, you don't have to, but the calculator can put more than one command in the same line. You just separate commands by a colon, and colon is above the decimal point. So I will do alpha colon, and then 1 store y. Now, when you have more than one command, sorry, I just realized this is in the way. When you have more than one command, that it only displays the output for the last command. And the last command was 1 into y, so that's why it's giving us a 1. But x is really back to 0. Okay, so I set my initial values. Now, I could retype everything in and store y just like I had, except that doesn't change my x for me automatically. I want to automate x as well. I want to change x and y at the same time. But the good news is x is changing by the same thing every time. So I can just say, remember x is going to change by 0.2? So I can say 0.2 plus x store x. That's going to take the old value of x, add 0.2, and then give me the new value of x. But before I have it go on, I'm going to go ahead, put a colon, because I'm going to put another command. And then I'm going to put that whole Euler's method formula. So that whole Euler's method again was y plus h, which was 0.2, times the derivative, which was sine x plus cosine y. And remember, before I hit enter, I want it to store that into y. Now, every time I hit enter, it's going to increase x by h and give me the new value for y. So 1.147, which, uh-oh, is not our value. Damien catches one other little last tweak we have to make. Before I get the answer, though, let's just remind ourselves what happened so people can think about this. So everything's still on the screen. Remember, we started with the initial value. 0 into x, 1 into y. That was our initial value. And then we increased x by h and had it evaluate Euler's method. Isn't that what we're supposed to do? What's missing? Super?
Did we use the wrong x?
What do you mean we used the wrong x?
Like it stored it and then it used that value, or?
Exactly. So, yeah, remember, I'll get you one sec, OJ. So remember when it's evaluating this value right here, the first iteration of Euler's method, it's supposed to be using the initial value, where x is 0 and y is 1. But look at what happened. Sure, we did say x was 0 and y was 1, but before it evaluated Euler's method, it already increased x to 0.2. And so it's using the wrong value of x. So we have one little tiny tweak to make, and then we'll finally have it. So Yonte, did you have a suggestion?
Yeah, same thing. Just you have to do the calculation first before it percent.
Well, the only thing is, if we reverse the order, it's not going to show us y.
Yes.
So here's what we're going to do. When we set our initial values, back up x by a step. So here's what I mean by that. So the initial value is supposed to be x is 0. I'm going to go backwards a step. And instead of adding 0.2, I'm going to subtract 0.2 and say negative 0.2 is x. Actually, here, let me clear everything so we can focus. Negative 0.2 into x, if I can type it, and 1 into y. So right now, x is the wrong value, but when I go ahead and say 0.2 plus x store x, that's going to make my first value of x be the correct value. We're going to be back at 0. And then I'm going to type in that whole Euler's method formula again. Y plus 0.2 sine x plus cosine y store y. Now when it evaluates it, it's going to evaluate it at the correct values.
Or we can do, like you said, you can do multiple process at one time. You can just put colon y, so it would print out y at the end.
True.
But you move
That is
the
correct.
0.2 to the end and then colon.
That's a cool way of fixing it too. Yeah. So now, whether you use Yoche's method or this one, if you hit enter, there's that first value. And here's the best part. Once you type it in to get the next value, all you have to do is hit enter. Enter, enter, enter. It's totally automated now. I mean, you got it. So cool. So that's what I would recommend. I'm going to write that down now in the notes. But does that make sense, this whole idea that we had to back up x? Actually, no. I'll put it on the next line. to enter Euler's method on the calculator. So remember your initial value for x? Make that back up by 1. So x sub 0 minus h stores into x. So your initial value of x minus h, you're backing it up one step, and then your initial value of y store into y. Type that on your first line, and then all you have to do is say x plus h, whoops, store x, and then y plus h, Euler's method at this point, store y. And then enter, 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 enter. So when you see those couple of problems on the homework where you have to do 10 iterations of Euler's method, do this, and all you have to do is hit enter 10 times and write the result each time. It's not that big a deal. Like I said, the most tedious part is going to be writing it all down. Ugh. Any questions about Euler's method itself or the calculator? That's it. Topic 1 down. 2 more topics. And we're done with anything new we're going to learn this year. Oh my God! This is crazy! Woohoo! Euler's method really doesn't get any harder.